I'm going to also introduce to you all the next big chapter that we're going to learn. Okay, similar characteristic between simply supported and cantilever beam. Okay, so why do I highlight that? Okay, why do I highlight it? So if I were to draw a simply supported beam, okay, on the left hand side is a simply supported. Okay, so I'm going to draw a simply supported beam. So this is my beam, and then we will have again point A, point B, and we have point C, right? And then we have a load P over here, right? So from here, we know that the structure, right, the structure will fail, right? The structure will fail at point B, right? The structure will fail at point B. So therefore, all analysis will be calculated right? I'll be calculating stresses at point B. Okay, at point B. Now, this, right? So this is my point C down here. Okay. So when we analyze the structure, we only need to analyze half of it. I repeat again, do you all realize that we only need to analyze either the left-hand side or the what? Or the right-hand side. You don't need to do both, left and right. You agree or disagree, right? You have done this structure before, right? In colleges, yes or no?
Yeah.
You only look at the left-hand side or the right-hand side. You don't need to look at both left and right. So why is that? Because this structure over here is also equivalent. Right? It bothers me, it bothers me when I was an undergrad or when I was in college. I'm like you guys, okay? I was from a college program, 3 years diploma. Then I went to do my engineering degree. Then I do my doctorate. And when I was doing this, like no one tell me why. Okay, I was so annoyed until when I'm teaching you guys have to know why, right? So now if I draw half of it, and this is just like force feeding, okay, that's it because I say so, and I don't want that to be the fact, okay? So this is equivalent, okay, this is equivalent when you have a load placed over here, P over 2, and this is a built-in, okay? And again, the distance from here to here is L over 2, L over 2, and the distance from here to here is L over 2. Point A, point B. And these two structures are the same. Okay. What is common down here? Anyone between the simply supported and the cantilever beam? Anyone? What's the most common thing that you can tell me between the two of them? Anyone, please? I'll give you a hint. At the cantilever,
the same, just the cantilever one has a anti-moment.
Yeah, no. What is the common? Think simple. For the cantilever beam and the simply supported beam, like what you see now, where will the structure fail?
At B.
At the
At B, absolutely. Right? The failure will absolutely occur at what? Yeah, absolutely right. Will occur at B, right? So if you have a ruler now, you bend your ruler far enough, where is it going to bend? Where is it going to break? Is it going to break at this end, or is it going to break where my finger is? You get what I mean?
It's fixed.
Yeah, where it's fixed, it will always bend where it's fixed. It's like when I jump. Why? Because you restrict movement. It's like when I'm in the 5th floor, when I jump from the 5th floor, where do I die? The 4th floor? No. 3rd floor? No. 2nd floor? No. Ground floor. Why? Because it restricts my what? My movement on falling down. Okay, so use that as an analogy. So we know that the structure, will also fail at point B. And why you fail at point B? Because maximum moment is at point where? It's at point B. Likewise, maximum moment is also at what? Point B. Okay. So now, let's prove it. Now, let's prove it mathematically. You know why mathematicians are so miserable? If the equation don't make sense, they get really, really miserable. Okay. But mathematics is critical. Why? With math, you don't need to do experiment to prove the hypothesis. You can use the math. If the equation are similar, it's proven. Bob's your uncle. It's a cheap way of doing it. Okay, right? It's a cheap way of doing Bob's your uncle. Unbelievable. So now, let's form the shear force and bending moment equation. Okay, so now let's look at the shear force. So shear force is our what? Have you seen this before? Yeah, we have seen this before. All right, let's form the shear force and bending moment. Okay, M equations. Let's mathematically do this. Okay, let's mathematically do this now. So we know that at point A, so we're going to have limits. So 0 x L over 2, right? So this is between point A and point B. Okay, so this is between point A and point B, right? So the limits is 0x to L over 2. Okay, so from here, we're going to draw our free body diagram. Right? So based on static analysis, you know that this over here is P over 2, right? So this is our point A. All right, because P is at the center, the distance are the same, both of them. So over here, you will take half of the load. Over here, you take the other half of the load, right? So from here, We have our variable over here, and this is our x. And then we're going to assume, later on, I'm going to explain, maybe in 2 weeks' time, I'm going to assume this assumption. We're going to assume the shear force is coming down over here. So V as a function of x, M as a function of x. Okay, so some of you ask me, Eugene, where is point B? Point B is over here. Okay, over there is point B. So our x is our variable. We're sliding. Okay, so from here, we're going to apply static analysis. Right? So the shear force equation is equal to positive summation of forces in the y direction is equal to 0. Right? So this is equal to P over 2 minus V as a function of x is equal to 0. So V as a function of x is equal to P over 2. Right? And then the next one, we're going to do a moment analysis. So the moment that we're going to take is the moment is where I'm drawing my dot now, my red dot. Okay, so we're going to take moment about the red dot. Okay. So again, static analysis, anti-clockwise, summation of moment in the z direction as a function of x is equal to what? 0. So the P over 2, so we're going to take moment at the red dot. We take moment. So the P over 2 multiplied by x is going clockwise, so minus P over 2 multiplied by x. Okay. And then plus by m as a function of x is equal to what? 0. Right? So over here, m as a function of x is equal to P over 2 multiplied by x. Okay. So now I'm going to sketch I'm going to briefly sketch our shear force. Okay, I'm going to sketch our shear force. Okay, so this is known as our shear force equation. And this over here is our bending moment equation. All right, so I'm going to sketch our shear force first. So this is my V, okay, my shear force. And then over here, this is my X. Right, so this is our X. So we have P over 2. So over here to here is L over 2. Over here is L. Right, so we have positive. You do this. Right, then at L over 2, it'll come down by P. So it's minus P over 2 down here. Right, it will come down by P. And then finally, over the other side, and then you go up at point L. The load support is P over 2 positive, so it goes back up to 0. Okay, so what you see down here is known as your shear force diagram. I hope I can draw it better, but I'm not. Okay, so this where you see that this is P over 2. When it reach over here, it goes down by what? It goes down, it pushes itself down by P. So down here, the bottom part is minus P over 2. And then at point C, you push it back up by P over 2. That's why your reaction over here, down here is also P over 2. His is also what? P over 2. Okay. So this is our shear force equation.